Now this presentation, it's, I've called it orbits and centerline plots. I guess it could be called prox probes, orbits and centerline plots. So it's really just describing, a little bit about how proximity probes work on large machines that have journal bearings, otherwise known as sleeve bearings or white metal bearings that you find in big turbines and other sorts of machines. So the idea is we'll just talk a little bit about, how those probes work, because we often find a lot of confusion around, even what the signal out is, what it basically all means. Then we'll get into where the orbit plot comes from and what the orbit plot is in essence telling you, and what the shapes can kind of tell you about the machine, but then also the centerline plot. Now, for some of you who are dealing with normal rolling element bearing machines, this, I guess I just want to expose to you a different world. There's a lot of people who really specialise in all this side of the world and hardly ever deal with rolling element bearing machines. In fact, often when you talk to people who live on this side of the world, they, I don't mean physically, I mean dealing with journal bearings and so on, they don't know very much about rolling element bearing machines. They don't sort of have the same idea in terms of reliability and fault diagnosis and so on. So I thought, well, this is a good chance, given most people are involved with rolling element bearing machines, to look at this side of the world. So we'll talk about prox probes, orbit plots, and centerline plots. So I should say, though, that this is a potentially deep and detailed topic, and various things that I'll be talking about really come from, Category 2 training, Category 3 and Category 4. Some of the illustrations and animations I'll show, we use in our Category 4 course. But I'm going to try and keep it simple. I'm going to summarise and generalise at times. So for those of you who, like Simon back there, who knows this stuff 5 times better than I do, just give me some looseness in terms just to sort of keep it simple, if you know what I mean. Okay, so in some of my animations, I'm going to be using a nice big rotor that we can use to explain what's going on. And that's actually a photo of it, from a big steam turbine. And so obviously that's the turbine part, and it'd normally be a generator hooked onto the end of it. You saw the pictures of generators with Simon's talk, and at the end you'll see a couple more from an animation point of view. But that's the sort of machine that we're dealing with. And if you thought about it in terms of, okay, this thing's mounted inside the steam turbine, you've got steam blasting the blades to make it spin and all that sort of good stuff, your normal thoughts would be that it is just sitting there spinning, and the bearings just hold it in place and it spins, and it's connected to the generator which generates the electricity. And of course there are other applications for these sorts of machines, but we'll just stick to this power generation one for the moment. But in reality we have to think more carefully about how these machines work, how they move, how they vibrate, and what's happening inside the bearings, because there are a number of things that we are concerned about. One is that inside the journal bearings themselves there's a certain amount of clearance. And as you'll see in a moment, journal bearings are very different from rolling element bearings in that they basically sit on a little pillow, if you like, of oil, a little oil wedge. And that's the whole way they're designed. You keep oil flowing in, they just sit there and glide on top of that oil wedge. And if everything's good, they stay in place. It's all very stable, reliable, safe, and everything else. But the issue for any design engineer, and also from a vibration point of view, is to have a good idea of exactly how that shaft is vibrating, how it is moving, which tells you a lot of things. It tells you, is there a fault condition like unbalance or misalignment or preload or some other sort of problem? Or is there an issue with the bearing itself? Do we have any stability issues? Do we have any rubs? The stability issue is that a shaft inside a bearing, or the journal inside the bearing, can start whipping around, can just start moving inside the clearances of that bearing, and things can go pear-shaped very quickly. So it's all about setting up a situation where that system is very stable and can continue to operate, and then be able to look at the data I'm talking about here, centerline plots and orbits, to get a sense for what sort of problem exists that may need to be corrected and whether there's an instability problem developing. So as I say, people with the Bentley Nevada systems and the metric systems and so on, that's the sort of thing they're concerned about. Of course, you can just put the sensors on and look at it from a protection point of view. For the amplitudes, which in this case we're talking about literal displacement, literal movement in that shaft within the bearing. If we see it exceed a certain level, we can just say, right, we have to shut down. It's exceeding those thresholds. But we would like to have diagnostic information as well so we can tell exactly what's going on. See if we have a design issue or maintenance issue or a process issue even. Okay, so from the rotor motion point of view, as I say, the simple way of visualizing it is it's just going to spin. But in reality, it's a long, flexible rotor. And if you looked at Simon's demonstrations out there on the bench, he showed how under certain conditions that rotor will flex. Think of it like a guitar string or something like that. It will flex. And while all the animations you will see are very exaggerated, we're not really seeing that much relative movement, but it is flexing at certain speeds. It's flexing like that. And when we think about unbalance and these sorts of situations, we've got to consider, what it is doing at any particular point in time. And when we look at orbits, that is one of the key things we're trying to find out. Just what is it doing along the length of that rotor? Is it moving as you see it like that, or is it moving differently? If misalignment will make it move differently to if it's unbalanced or other conditions. So, I guess that's another sort of view of how the rotor vibrates. Now, again, very exaggerated, but we have the bearing itself, and we can focus in on the journal within that bearing, and we're interested in two big things. How is it moving? Now, if you can look at that, you can see it's moving in a circular motion, which you may consider is just the normal motion. So that's one question. And the second question is, where within that bearing is it moving in that circular motion? Right there, just for animation purposes, I've put it right slap bang in the middle. And you might say, well, is that where it's supposed to be? Is it supposed to be there? Is it supposed to be down the bottom? Is it supposed to be to the left or to the right? And that's what the design engineers and the people who focus on this sort of vibration analysis need to understand. Where should it be? And if it's not there, what are the consequences? What do we need to do about it? So that's the thing we're interested in. Now again, I'm exaggerating the clearances and so on, but this is more like what it looks like. As in, we've got that rotation, and in this case I'm not showing any motion of the shaft, but it forms a little oil wedge underneath. And that is what separates those two surfaces. So it just sits on that oil, and as it spins, you can sort of see how it's sitting. Obviously, it's critically important that we keep the lubricant up to the bearing. Without that lubricant, we've got those two surfaces rubbing, and that's not good, as you can probably imagine. We can wipe the bearings, as it's called. But anyway, so that's the situation going on inside the journal bearing. That's the measurements we want to take to see where is it, how is it moving, is it all good. But as we get more into it, and I'll come back to this towards the end of the presentation, if you saw Simon's demonstrator out there, we had the first mode, and this is the second bending mode, and that is, in effect, what the machine is doing. When you run it up above that second critical, that's what it's doing. But how do we know what it's doing? That's what the vibration readings tell us. That's what the orbit really tells us. And we need some phase information as well, so that when we do look at the bearings at either end, for example, we can tell, well, is it moving in phase or out of phase? That's the sort of thing that we would like to know. So let's take a closer look at the measurements. Because I want to know where that shaft is within the bearing, or where the journal is, we use two proximity probes. The two gives us the ability to triangulate. We can sort of say, well, it's a certain distance from the one probe to the shaft and the other probe to the shaft, and you can tell based on those relative distances just where it is. So that's what our two proximity probes, normally mounted 90 degrees apart. And that way we can do our triangulation. Sometimes for physical reasons and design reasons they may not be exactly 90 degrees, but then the readings have to be compensated, for that. But we'll keep it simple, we'll just use the case of 90 degrees. So how do those probes work? Now we don't need to go into a great lot of detail, but basically they are effectively measuring the distance between the tip of the probe and the surface that they are looking at. Now these might be mounted right next to the bearing or a little further away, but they are looking at the surface of the shaft, and as I say, as it moves back and forward. Now, basically it requires some signal conditioning. You can see an example of that with the little device there, and it's a high-frequency oscillator, which is used to induce eddy currents into the surface of the metal. So as that shaft is turning, it's inducing those eddy currents, and basically the amount of energy required to do that differs as the gap changes. So we have this oscillator, which is what the device is used for, creating these eddy currents, and basically the sort of signal strength tells us how that movement is changing. So, point is though that you've got the probe, you've got the shaft, and some relative movement, and we've got the gap, the gap that originally existed, and then the movement that we have to deal with. So that's one little point I want to illustrate here. So in this case, you can see, just really keeping it simple, we're using a dial indicator instead of a proximity probe, but you can imagine as this shaft turns and I exaggerate the motion, we see the nice little sine wave that we're all familiar with. But of course, if I was to push the shaft over here, this side of the bearing, and spin it, okay, we might be having a rub here, but you can see I'm still got the sine wave, but you see the sine wave's been offset in this case. If I drag it back closer to it, we've still got a sine wave because the actual movement of that shaft is the same in each case, but now that it's closer to the probe, we get this offset. And that's why when you look at these signals, there's an AC part and a DC part. Instead of a dial indicator, obviously we've got the proximity probe, which is sensing that distance as I described. And then if I just look at the AC part, it is just giving me that dynamic component. Doesn't matter exactly how, but it doesn't matter therefore whether it's, over this side of the bearing, over that side of the bearing. The AC part is just the dynamic motion. On the other hand, the DC part is basically the gap between, if you like, the center of rotation and the probe. So, even though that shaft's moving, because of the way the signal conditioning and processing works, we're really just looking at the average center position of the shaft, back to the probe. And so in this case, it is sensitive to where this rotation's occurring. And that's something we want to know, because we want to know, it's very important to us, whether it's rotating basically around the center of the shaft, or the left, or the right, or down here, or over there. That is very important to us from a stability point of view, and to diagnose things like misalignment and so on, because it's pushing the shaft over perhaps where it shouldn't be. So that's the AC part and the DC part. One other little thing that I find confusion with is when you look at a chart for one of these sensors, they'll tell you the voltage difference per micron or mil of movement. And so you get a graph like this, which basically shows how many volts relates to how much displacement. So we've got displacement along the bottom. Let's go microns. So we've got displacement along the bottom, and that's just the conversion factor, the calibration factor. So as my shaft moves, the distance is changing, which relates to a changing voltage, and therefore we see that changing voltage. But a lot of people, it gets confusing, because when you look at the chart displayed that way, which is the conventional way they're produced, you notice that it's higher negative voltage as you go up. And if you look at the movement, if I just turn that off for a second and zoom in, as I move it towards the probe, it sort of looks like a lower voltage and it looks like a high voltage, and you start looking at the sine wave and saying, well, does that mean it's closer or further? It did my head in anyway, so I'm sure I'm probably not the only one. So that's why we made this cute little thing here to explain it, because the easier way to think about it is, number one, flip the graph over, and that way, you know, as you move it closer, it's actually moving closer to zero. As you're moving it down, it's a higher negative voltage. But now if you think about the sine wave that you will see in your software, that's the sort of motion you're looking at. In fact, we can, you know, rotate it. Now the other thing you'll see, because we're using the AC coupling and just looking at the AC part, that's in effect what we have done. So now when we're rotating it, it's rotating around that 0 point. So hopefully that makes it a little clearer what the signals are you get out of one of these proximity probes. The DC part is the gap, the AC part's just telling us about the movement. Okay, so that's, I think I said enough of that. One other little comment I'll make is that, you know, the probe is sensitive to the distance, but because we're setting up these eddy currents, it's very sensitive to the makeup of that shaft. So if the shaft wasn't perfectly flat, if the metallurgy of the shaft wasn't perfectly uniform, if there was any residual magnetism, if there were any scratches or any problem like that, well, that's all reflected in that same signal. Because as the shaft's turning, in addition to seeing the movement, we're seeing the results of, you know, what some people call, you know, glitch, the glitch that's on the, or the imperfections that are in the shaft. So what they do is they turn the shaft at a low speed, you know, 100 RPM, something like that, at a low speed where there's not going to be any vibration, any movement, no dynamic movement, no movement at all. It's just turning. So you know that the displacement is constant. So then what you do is you measure a signal at that time, and you get, which is shown here, you get an ugly looking recording, which is the imperfections, the scratches and whatever. And then you can do a couple of things with that. You can use it as a vector or use it as a whole recording. But basically, from now on, when we record from this machine, we subtract that out. Because you say, well, that's all the glitches. We'll remove that from the signal that we're ultimately going to use to analyse, and that cleans things up. So that's sometimes called glitch removal or slow roll compensation, possibly by other names as well. So that's something when you ever look at one of these graphs, you'll see, has it been compensated? And that's what they're talking about. It'll often be written on the plot. Is it compensated or not? So if you do see something that looks kind of ugly, well, then you know it's really from the machine and not just from the, you know, the way the data was collected. So that's what we end up with then. We've got our two probes, shaft spinning but actually moving. And but we'd like to have one more thing. I mentioned before we'd like to have phase so that we can see what's happening at different points along the shaft, see what's happening. There's other reasons we would like this once per revolution signal. So without going into a great amount of detail, we add a third probe, but just one for the rotor in a different plane. So it's not looking at the same point on the shaft as the two other proximity probes. It's looking at a keyway. So as that keyway goes by, it sees a very distinct difference in the displacement, and therefore that's a timing signal that we can use. So whenever you look at orbit plots and all this data that we're talking about, you will see a little dot on the plot, which basically says that is when the trigger fired. That is when the keyway went by. That's our timing reference, which helps us for a whole lot of reasons, some of which you'll see soon. Now, so when we take our phase readings, this is basically what's happening. So the shaft's turning. Here are my two time waveforms. So this one, this time waveform relates to this probe. This time waveform relates to that probe. And then we've got our timing reference. So if you watch for a moment, the keyway goes past this probe and it triggers it. And there's the little dot, and then it waits until the heavy spot, let's just simplify things and just say the heavy spot, high spot, just keep it simple. When it goes by, that's the peak in the signal. And so from a timing point of view, when we get our phase readings, that's what's happening. We see the keyway go by, start counting. When the high spot goes past the probe that we're looking at, we see the high spot, boom, that's the peak of the signal. That's our phase reading. And just to sort of make it a bit easier. So in this case, we've gone past, let's switch to the this probe. So now we can see the high spot just went past the X probe, and so therefore it's 170 degrees in this case. Now you may think, well, you've got them 90 degrees apart, of course the phase angle is going to be 90 degrees difference, if I switch between these two. Now that's true only if those two signals are the same amplitude and there's no other phase issues. As soon as we get into, well, everything else, the actual signals are not the same. They're elliptical, they could be figure of eights if you compare them, and we don't see that 90 degrees phase relationship. But you'll see more of that in just a moment. But anyway, so that's one of the ways we use this key phaser. We get this once per rev tach, and we can therefore get phase readings from that as a result, and that's what we look at. When we get into rotordynamics, this whole question of what this red dot means, I used two words there, heavy spot and high spot. That's really what Simon was talking about before with resonance. Those shift apart as soon as you start going towards critical speeds and so on, but let's not go there just yet. In fact, at all today. So we've got this wonderful data, and now we're going to turn it into information, which should make the previous speaker very happy. It's okay looking at these two sine waves. It tells us something. We can certainly look at them. We can even look at a spectrum of it. If we had more time, we could look at a few other things with that data, but we'll just focus on orbits for now. What we really want to do is say, what is that shaft doing? And we've got our two probes watching it carefully. What we're really interested in is, what is the center of that shaft doing? And in this case, you can see it's moving in a circular motion. And that's exactly what the orbit is telling us. What is the center of the shaft doing? Now, okay, we might be measuring the outside of the shaft, but it's round, so we can project in our minds back to the center of the rotor. So, if the rotor is moving in a circular motion, and we compare those two signals from the X and Y probe, we get an orbit, a round orbit in that case. And that's exactly where this comes from. Now, what I did in this animation, I said, well, if we had measurements at multiple positions, we can then compare those and see in this case, the orbit's in the middle, there's more movement than the ones on the end. Now, because of the machine designs, you may not have data available from points like that. It just depends where the bearings are and where you can get the probes in and so on. But anyway, the point is the probes, the orbit tells us what the shape of the movement is, circular in this case, and also by comparing them, we can tell how that shaft is moving. And we can tell in this case that it's, it seems to be bending in this particular example. And just to clarify, if I take two sine waves offset by 90 degrees, plot them against each other, then you get a circle. That's the origin of the orbit, you might say. So here is the situation. We've got our shaft moving. Now again, I'm exaggerating the movement just to make it look easier, but because it's moving in a circular motion, I will get two sine waves that, the fact that I got two sine waves that are 90 degrees difference in phase tells me that the shaft is moving in a circular motion. Now, of course, we can have a little play with this. If I experienced a higher amplitude vibration in the X direction, then that would tell me that the shaft is not moving in a circular motion. It's actually elliptical. It's actually moving more like this. And that's more typically what you're going to see, because the shaft is freer to move horizontally than it is vertically. In a moment, we'll talk about bearings just a little bit. If you've got a round bearing, you get one sort of typical orbit shape, but with tilt pad bearings or with lemon or elliptical bearings, there's more freedom to move, if you like, less stiffness in that horizontal plane, and therefore it can move more. Now, one other little tricky thing is that if we actually superimpose we'll just slow it down, we'll put our prox probes on in our key phaser. So there's our key phaser watching the probe, the shaft go around, and only it is seeing the key wave. And our two probes are watching the movement of the shaft, and I'll just shrink it down to make it a bit easier. But the probes themselves may not be mounted at that sort of 3 o'clock, 12 o'clock, as we see there. They may be mounted more like this, or, any number of ways. Just depends on the design of the bearing, where the split line is, and a number of other things. So basically we have the two probes, and most of the software you use sort of does all this compensation, so that when you look at the raw signals, that is what came from the probe. But if you look at compensated data and so on and look at the orbit, you can orient yourself to say, well, okay, that is vertical and that is horizontal. But do check with your software whether that's really what you're looking at, horizontal, vertical, regardless of where those probes are mounted. But, and that all depends on the shape, what sort of movement you're getting. And this is one of the tricky things too, that if you look at this, you see that the two signals have a certain amplitude, and in fact that the amplitudes of both of them are somewhat similar the way I've got it right now. But if the probes had been mounted here, you might notice that now the Y signal is much lower in amplitude and the X signal is now much higher in amplitude. So this is something you have to keep in mind when you set alarm limits and all of that. What are the probes actually seeing? Are they seeing that full motion, or are they just, seeing it from their perspective? So depending on how that orbit changes because of the forces on the machine and so on, what are we actually going to see? And that's why there's a parameter called S max, which from the two signals says, well, your maximum displacement is what we are actually looking at right now. But in any case, everything that so we start with these two signals, and we can create the orbit from that. Now, the other important point to make is that what I'm really showing right now is just the 1x vibration. It's just the vibration associated with the turning speed. But just like all other machines, we can have vibration at 2x, 3x, we can have vibration at half x or 0.38x and so on, just depending on what's happening with the machine. And that's, again, why we need to know what we are looking at, because we can take these signals and, for the machine doing the very same thing, we could get two different orbits, and sometimes totally different orbits, because one is showing us the raw signal, the direct signal from the two probes with all of the 2x vibration, 3x vibration and so on there as well, versus just the single 1x signal, if you see there. And so, in fact, I'll come back here. I thought I had a slide. You'll see it in a second. We call the signal at the top is often called the direct. So it includes everything versus 1x filtered. The filtered vibration is the one at the bottom. And anytime you see an orbit, it's really important to know, am I looking at the 1x filtered vibration versus the direct signal? Because that tells you more, it allows you to interpret it. So basically then, we look at the orbit and say, well, what does that tell us about the machine vibration or the rotor's vibration? In this case, I've got a nice little orbit, a little bit elliptical, just shows there's a bit of movement there. Of course, if we had some unbalance, and that was the primary force, then we've got a bigger orbit because there's more movement, and perhaps, as I mentioned before, it's less stiff horizontally, and therefore it moves more horizontally. So we actually get a bit more of an elliptical orbit. But again, we, like everything else in vibration, we can interpret orbit shapes, and we can look at how vibration has changed, or therefore how the orbit has changed, to get an idea of what's actually going on. So, in this case, you might look at that and say, okay, well now the ellipses, or the elliptical shape, has tilted on its side. And again, it's one of these classic cases where we can become data junkies and just look at that and think, oh, is there a little chart book I can look at which tells me if the orbit looks like this, this is what it means. But on the other hand, we can step back and say, well, we are looking at how the center of the rotor is moving. What would make it move like that? Well, if it was moving in a circular motion and I put some force from that lower quadrant, from sort of like 4 o'clock, if I pushed up, now it's less free to move in that direction and more free to move tangentially to that direction. And that's what's happening. So maybe there's some sort of preload, maybe there's misalignment, and that's what's causing it to do that. And in fact, you know, if we push the misalignment too hard, we can actually have it move in like a figure 8. Now we can play around with little signal generators and that little simulator I had before, and we would see that if you had the right combination of 1x vibration and 2x vibration, you can make these sorts of shapes. You can make all kinds of shapes if you got the time. But rather than just thinking about it in those terms, you can just look at it and say, well, what would cause that motion to change in that way? In this particular case, it's not super clear, but it's moving, but then it rubs, and you can see that it's free to move for a certain portion, and then it's rubbing, which restricts that movement. And again, looking at the orbit, we can see, we can interpret what's going on. In some cases, we can have a rub that causes a little bounce sort of movement, and we get something like that. So the movement and the shape tells us quite a lot. The other thing, which we won't go into in any great detail now, is that we can look at a static orbit. So here I'm looking at vibration that is less than half running speed, which happens to occur when we have something called oil whirl. This is an instability. This is the bearing, moving around quite violently, well, basically around the inside of the bearing. Oil whip is when it causes the whole rotor to sort of go into its first bending mode. Oil whirl is just the shaft moving around the inside of the clearances. But it does that at less than half running speed. And again, this is something we could spend a lot of time talking about. But a stationary orbit, if we just looked at the 1x orbit, you'll see that it has 2 dots. And you'd say, well, why are we seeing 2 dots? And that is because in the time, remember I said it was 0.38 of running speed? Well, in the time it's taken to rotate once, and therefore 1 trigger from our key phaser, we've had 2 big motions. Think of it that it's travelled around the inside of the bearing twice. It's physically gone around. It's 0.38, not half. If it was half, it would go around exactly twice in the time it took to get 2 of these triggers. If we look at the direct, then we've got a combination there of the motion and the submotion, because we're looking at all the vibration. But if we look at this in live mode instead, we will see that the orbits, if we're looking at a live orbit, not only do we see our 2 dots, which aren't completely opposite each other, we would see the orbit rotate. And if we know the direction of rotation, that's that big black arrow, and we see which way the orbit itself is rotating, which is against that direction, we therefore know that it's less than half the running speed. Now again, we could talk about that for a while, but it's just one of the things that a person involved in this science has to understand. How many dots am I seeing? And if it's live, which way are those dots moving? What's the precession, if you like, of those dots? So it's all good stuff. We can therefore tell, using the spectrum as well, but looking at the orbits, looking at the precession of the dots, we can tell what's going on. And there's a lot of other things we could talk about here, but enough said about that. So the orbit gave us 1/2 of the picture, which is good. It's telling us how the shaft is moving, but it doesn't tell us where inside the bearing it's moving. Now, as I say, we don't have a lot of clearance, but where it moves is critically important to the stability of the machine. So this is a typical run-up plot looking at a centerline diagram. So imagine, if you will, that a bearing has certain clearance. In other words, if you sort of grab the shaft, or at the journal, and moved it around the inside of the clearance, it's only got a certain amount of movement that it can make before it rubs. So that's what that circle there is. If it was a circular bearing, we got a certain amount of movement. That's how much it can move. Now, I'll illustrate this in just a moment to make it even clearer. But what we're doing is we're saying, well, where can the centre of the shaft move? So imagine putting a circle around the centre of the shaft, saying if the centre of the shaft moved above this point, it would be bumping against the top. If it went below that point, it would be banging against the bottom, or the left side or the right side. So what we're seeing here is that as the machine started up, the centre was at the bottom of the bearing. It's just resting in its bearings. They may pump oil underneath. It starts turning, and as it gets faster and faster, it actually lifts up and moves away from the side of the bearing, and it's got that nice little oil wedge sitting underneath it. So where did it move? Did it move to the right place? So in this case, you can see it lifted up as it got faster and faster, and that's what those little speed markers are, until it finally stopped at that point. Now, for a shaft rotating in this clockwise direction, that's actually right where we want it. We want it down in that little quadrant there. And again, this is just what guys who are monitoring these big machines, these big process machines are doing. They're very keen watching what happens. So let's understand that just a little better. There's our orbit. And remember what I said about an orbit, that's where the centre of the shaft is moving. So imagine if I had a big shaft and I put an X sort of in the middle, and that's where the shaft is moving, so that's what the orbit tells us. So if we were to sort of zoom back, if you like, well, there is the shaft with the centre moving in that plane. But so far, we know it's elliptical, that tells us something, but we don't know where it's happening. So what we'd like to do is superimpose over that where the bearings are. And so in this particular case, you can see this is moving in that orbit right in the centre of this big bearing there. And if you look at it, it's that yellow circle there is the available clearance. And this is where it gets confusing. But if I grab the centre of the shaft and try to move it, so I'm going to bump into the bearing there, oops, you notice that the little cross is right on the edge of that yellow area. If I drag it over the other side, bang, I'm into the side there, and again I'm on the other edge. So I can't move the centre of the shaft outside of that yellow circle, and that's the circle that we see on the centerline plot. And then it's just all about, you know, where does it move as it starts up and where is it sitting? Because for these sorts of bearings, depending on which way it's rotating and so on, just depending on the type of bearing, we do want it sitting in here with that little wedge of oil underneath. Because if it was sitting up here or over there, given it was rotating in the clockwise direction, that would be bad. That would mean it's unstable, potentially unstable. It might go unstable. So again, people involved with all of this, you have to watch this sort of thing to make sure everything's cool. With certain bearings, like tilting pad bearings, actually you expect it to basically ride pretty much straight up. With tilting pad bearings, they ride in a different place. So anyway, all this data serves to show us that. And so, in this case, it's sitting there moving in the centre of the rotor, and we happen to know that that's an unstable way to operate the machine. This particular sample of a centerline plot overlays the orbit with the movement. So the circle is the available clearance. The centre of the shaft, when it was just slow roll turning, is sitting down here. It gets faster and faster and faster and faster, ends up right up here in the middle, and there's the orbit superimposed. This has tilting pad bearings, so it's a good thing that it's moved up there. Anyway, that's basically what the centerline plot tells us. Where in the bearing is it moving? And we can look at a few samples. We can see, how it's moved in this case. It's sort of moved about where it should, slightly elliptical. It's all good. Now you can see that the centerline plot's told us that it's moved in a slightly unusual path. It's sitting high and a bit to the left, and the orbit is more elliptical, and that tells us there's some sort of preload or misalignment. And this one even more so. You can see it's pushed right up against the edge of the bearing if you look at that centerline plot. And that's what all this data is there to tell us. Now, very briefly, as Simon talked about with resonance, and you saw out there on the little demonstrator, if you consider this rotor here as just one big long chunk of steel, and if you walked up with a hammer and hit it, if it was supported at either end, you'd know from a resonance point of view that it's going to resonate, like this. If I just whacked down on it, okay, it's going to do this. but it's also going to do this, and it's also going to do that, and I need rubber arms to show all the rest of them. So there's all just the different modes. Well, the fact is that these long rotors do all of that. So at low speed, they stay rigid. But as they go faster and faster, then they start moving in this first bending mode. Instead of like this, it's like so. And that's what we see, in the animation. That's at or near or, during the first critical. So it's the first bending mode. Now, the term first bending mode, we could discuss that forever, but just keep it simple. We'll just call it the first bending mode. And then as it speeds up, it's going to approach the second bending mode and vibrate differently. And again, knowing the dynamics of the rotor, knowing how we're operating it, and looking at our orbits and all that, we can tell exactly what's going on. And this is all important, if you're going to be balancing the machine and all the rest of it. But this is what the data's telling you. But we've got to remember that we've actually coupled this thing up to a generator. And so now we're dealing with the whole machine. Now what we're actually seeing is, we went through the process of modelling this whole thing to see exactly how it would how it would vibrate at different frequencies and so on. But there we've got, the first bending mode of the steam turbine, and you can see the generator is just spinning happily. But at a different speed, the generator is going through its first bending mode, and the turbine is happy. Anyway, we could talk about that a lot more, but we can, go through and model all this stuff if we like, but we can look at the data and just see what's going on. Anyway, bottom line is, using the 2 prox probes and the key phaser, we can tell how the shaft is moving, where it's moving inside the bearing, and therefore understand if we've got any mechanical issues like unbalance or misalignments and so on, or if we've got either existing or potential stability issues as well. And that's my presentation. Any questions?
Yeah, Jason, I've got a couple of comments. One is the positioning of the prox probe relative to the centre line of the bearing is quite critical, because if you've got one on the outboard end and one on the inboard end, you'll get a phase shift due to a bend.
Yep.
So you've got to make sure they're both in the same relative position and not on the neutral point through the bearing.
Yep.
Another one is the slow roll vector that you mentioned. You've got to use that if you're doing any balancing using prox probes, otherwise you won't get a proper balance.
Yep.
And the other one we've come across a couple of times now is don't put the key phaser notch in line with the XY prox probes, because it don't work.
Oh, okay. Because
the probes see the notch as well, and you'll get a vibration.
in line in the same plane. Oh, absolutely, yeah.
It'd be surprising the number of machines we've actually seen that notch in line with the same prox probes.
That's crazy talk, yeah.
It sounds crazy, but we've seen it too many times now.
You sort of wonder what they were thinking.
Another one is eccentricity is a low-speed bend, and that is also used with a prox probe, so don't null it out. It can indicate a bend on the shaft, not a true a run out, a slow roll.
That's true.
And the other one, I would have an argument with you about the oil well filter. The oil well filter, where you see 2 dots, is not once times filter. It must be 0.45 or similar. If you have a once times filter, you will only see once times.
Well, if you're looking at the movement, at the running speed, well, if you're filtering at the running speed, you are seeing this movement, but during the time of that excursion, because remember the orbit's not just showing one rotation, it's showing a number of rotations of the shaft. And so those probes, those dots are going to appear 2 per rotation.
No, not if you're filtering at once times. If you're filtering at once times, all you'll see is the once times orbit, and you'll filter out the half speed oil well function. Yeah,
but it's physically moving at 0.38 of the speed, so it's moving like this.
I agree, but if you're only filtering the once times out, you'll only see 1 key phaser dot. If you filter it at 0.45 or the orbit speed for the world, then you'll see 2.
Well, let's talk about it separately, because we could be here for a while. Yeah, I think it depends on the system, perhaps. Yeah.
Prox probes, what's the limit of their reliability in terms of shaft RPM? What happens when you're up to 10, 12, 15,000, 20,000 RPM?
I don't know. We got some suppliers. I know that they're used on very high-speed machines, very high-speed compressors and so on.
The data you get is rather difficult.
Yeah.
One of it's something to do with the linearity of the drops group.
I couldn't tell you, to be honest. I couldn't tell you. I know that they are used on extremely high-speed machines.
Yeah, I played around with them and
I think the main issue with high-speed machines is that the frequency, you don't get much displacement for the vibration frequency.
Yeah.
The displacement for very high velocities is quite low, and that's the danger, because velocity is actually a measurement of the energy.
Yeah. Yeah. Well, there is that too. But I think, if you're trying to see what the shaft is doing within the bearing, one question that comes up so frequently is if you took an accelerometer and put it on the outside of the bearing and converted it, double integrated it down to displacement, would you see the same as what you see with a prox probe? Now, although they're both integrated to displacement, one is looking at, if you like, the displacement of the bearing cap, and one is looking at the displacement of the probe, which is probably physically attached to the bearing cap. Again, we could talk about this forever, but looking at that relative movement to the shaft. So if we had a stationary bearing and the shaft moving inside, then the accelerometer signal would say no displacement, and the displacement signal would say yes, there is displacement. You can imagine a different situation where for some reason the shaft is actually spinning, let's just call it without motion, and the bearing cap for some reason is moving. Well, the proximity probe is going to see the relative movement between the probe, the house and the shaft, but the accelerometer is going to see the same thing. It's seeing that motion. So people will often use the accelerometer as well as proximity probes to sort of zero out what is the shaft doing relative to ground. But they will give you different results. The other issue is that the transmission of the vibration, if you like, or the motion through that oil wedge to the bearing, to the housing where you're taking those measurements, there's a lot of dampening that goes on. And that's another reason why we want to take that measurement, to really see what's happening.
One more question.
As I say, we just summarised a whole Cat 4 course in the last 30 minutes, so that's why I had to generalise on a few things.
Yeah, Jason, I'd like to make one comment on the type of instrument or the sensor itself. So it's pretty much looking into the material. It's not really staying at the surface. So if you have some material inhomogeneity, it will tell you, it will give you a false reading of this actually change of the distance. So it's another point just to keep in mind, even if it's perfectly circular, so to say.
Well, that's what the glitch removal's for.
Yeah.
So any non-homogeneity, try and say that a few times.
Right. So sometimes it's useful to use laser triangulation in addition to that, just to see if it's really a material inhomogeneous effect or if it's a surface effect about the glitch removal.
There are different probes now that are being used to look at that displacement, but proximity probes are the most common sort of out there for these sorts of things.
It's just about knowing your sensor, and the sensor, none of these sensors is ever perfect, so they always have some side effects, and sometimes if you're running into strange effects, to take it into consideration.
Yep, good point.
All right.